This is just a snapshot of hyperlinks. Okay, and you can see the when you change the structure of the macrostrip. This is the macrostrip. This is the strip line. Okay, the strip line has two references, one on the top, one on the bottom, and then the trace is in the middle. Okay, that's another. So if you have a trace in the middle of your printed circuit board, and then it's called strip line. Okay, if the trace is on the top or bottom of the board, it's a macrostrip. Okay, so the hyperlink software should be able to calculate line parameters for both cases. And of course, there are some empirical formulas or approximations. I just list them here for completion. So way before we can do software simulation, some of these formulas are pretty useful. Nowadays, we don't really need to use this formula anymore. We can just go to the and just start a computer software. We can get all the parameters. Okay, so I just listed them here and also compared this empirical formula. Okay, this is an empirical formula from another article. I compared this calculation with hyperlink's calculation, and then I found that they are more or less the same. Okay, so and from the formula, this calculation impedance should be 59.8 ohms, and then the hyperlinks gives 61 ohms. Okay, so it's very, very similar results. Okay, and then this is a curve that shows dielectric thickness and the characteristic impedance. Okay, the higher the dielectric thickness, the higher the impedance is. Okay, because actually it's reasonable because we know the characteristic impedance is a function of capacitance and inductances. Okay. So if you have a macrostrip here, this is the height of the dielectric. Okay, the higher the dielectric, the less capacity you have, right? Okay, if the capacity is smaller, then the characteristic impedance is higher. So that's basically this is what is shown here. Okay, this is again the approximation formula for macrostrip line, which is the trace in the middle of two ground references. Okay, and this is a asymmetric strip line. Okay, you can also simulate transmission lines with discrete component. This is lab 1. It will take some time for you to do. Okay, so that's why you need to really spend some time to figure out. Actually, this is very similar to what you can do with for lab 1. Okay, the lab 1 is to use discrete component to simulate the transmission line. Okay. So this is the concept. The concept, you have a transmission line. And you're going to replace this with inductor and capacitor network. So this is basically what. And then you're going to simulate this to find out how close this network can be used to approximate the transmission line. Okay. The key point is, because this is a so-called discrete component, right? We use discrete component to simulate a continuous transmission line, and then of course you introduce errors. Okay, it cannot be exactly the same. But how many components do you need to use? Okay, it depends on how you want to divide this line into small pieces. Okay, and let's see this line is 1 wavelength long. Okay, so if you take a snapshot of this, you can get this voltage distribution, right? That's 1 wavelength. Okay. So how fine do we need to divide this transmission line to get a good approximation? I talk about this concept of electrical short or electrical long, right? So how many pieces do we want to divide this transmission line to get more or less a good approximation? Assuming this line is 1 wavelength long. Do you remember the so-called rule of thumb? 1/10. That's right. Yeah. So the rule of the thumb. Okay. And that's what we used to measure distance, right? Remember in physics, you learn how to measure distance in physics with your thumb. Have you done this before? No? To measure distance with your thumb. And that's a very old way to measure distance. And then that's where this idiom comes from. So it's approximately, okay, 1/10, because if you divide this 1 wavelength in 10 pieces, so then you more or less you can assume that within this piece the voltage is the same. Okay, that's what the underlying assumption of this, because at this point the voltage is a single voltage, right? At this point the voltage is a single voltage. So, but this is a physical transmission line. But if you divide it smaller enough, then you can see that the voltage between this is more or less the same. Okay. Of course, each of this piece is 1 LC. So you need 10 pairs of LC to approximate this transmission line. Okay. Of course, the finer you design it, you divide this, the better the approximation. Okay. So this example basically shows you how you relate field and circuit. Okay. This is the field, and then we can go from field to circuit. Okay. In this class, as much as possible, we're going to use circuit. Okay. But because of high speed, we're talking about high speed transmission. So circuit is approximation of the field. Okay. But how well can you approximate the circuit of the field? It depends on how well you understand the field, right? Because if I ask you to approximate a transmission line with a LC network, and you don't understand the wavelengths and then electrically short concept of electrical short and so on, you will not be able to know how well you can represent this. Okay, so I always comes back to explain to you whenever we model something like inductor and capacitor. Okay, inductor, capacitor are circuit concept, right? Voltage, current, they're all circuit concept. Okay, and but actually there's no circuit in nature. Okay, electric energy and magnetic energy, they are transmitted as fields. In your iPhone, in your cell phone, everything is field, right? There's no circuit. Think about it. Circuit is a model. Circuit is a model of a field. But whether the model is correct or not depends on how well it can represent the reality. Okay, so and of course in field we have E and H and mu and epsilon. Okay, electrical field, magnetic field, magnetic field properties and electrical field properties. So we basically have a structure and we also have geometry. Okay, structure. So we're dealing with, in field, we're dealing with space and time, right? But in circuit, it's time only. See, you don't see space when you do circuit simulation, when you do circuit, but when you do field, you have to worry about both space and time. Okay, geometry, structure, material properties, and then field propagations. Okay, so that's why circuit is much easier to deal with, but circuit is a model. Okay, is a model of the field. All right, so this again, this example is one example. Okay, where I use LC circuit to represent a piece of transmission line. Then you can do a simulation to find out how well that approximation is. You can see because of approximation, it will introduce all these ripples. Okay, ideal transmission line will not have any ripples, but once you represent that with discrete components, you can see some ripples. Now I'm going to introduce you to what this class is about. Okay, and I copied this from another professor at Stanford University. He's a chair of the computer science at Stanford University, William Daly. He wrote a book on this high-speed digital design topic. Okay. Basically, what we want to do is to understand physical design. Okay. Digital design, you all taken digital logic design, right? FPGA. Have you used FPGA? Verilog or VHDL? Have you used Verilog or VHDL? Verilog. So you know logic design. You know gates and flip-flops, sequential circuit, combinational circuit, and so on. These are called logic designs because it's nothing to do with physical world, right? It's more like mathematical design. Okay? But then once you want to put it on the board, then you have to face electrical issues. Okay? So you have to understand system level issues. Okay? And you have to understand there's noises. Okay? So there's noise margin, there's timing margin. So and if your circuit do not meet these requirements, it may not work. The circuit may not work. Okay? And also you want to run your circuit as fast as possible. So once you purchase an FPGA chip, that cost is already fixed, right? So if you run it at the highest speed possible, then you can get your money back as quickly as possible. Okay? So there's a signaling speed, there's a synchronization problem, there's a failure problem, and there's also power distribution problem. So basically this class is about how you can make a circuit on the board and make it run reliably. Okay. I like to follow cell phone industry. Okay, and then some of the issues actually in cell phone designs about high-speed digital designs. Okay, of course, most cell phone, none of the cell phone company will tell you they have problems, right? But they cannot do a very well design. They cannot make it design reliably because they have electrical high-speed issues. Okay, but I'm not sure these three companies have that problem. But Nokia, I have a Nokia phone here. Okay, and this is the trend from 2007 to 2011. Okay, the percentage of their shares, the three companies, assuming the company has 100% share, right? And then how they Nokia used to be, notice this is Nokia, the dark one. Notice how Nokia is going down. And this blue is Apple, this light blue. You can see Apple is going up. And this very light one is Samsung. You can see Samsung is going up from here too. Okay, so and that's interesting because both Samsung and Apple, they both work with University of Missouri. Okay, and Huawei is also one of the partners of University of Missouri, where Professor Gui Liangqi just came back. Professor Gui Liangqi spent 1 year there. University of Missouri has a center for high-speed design, and the EMC is the best center in the world. Okay, but Nokia is not a partner there. Okay, maybe there's something there. I don't know, because Samsung is very active. Okay, Apple is very active. Okay, and then Samsung, of course, is doing so well. Okay, it sold 16 million units of this their Galaxy S smartphone. You can see how 2 years ago they sold 24 millions, and then last year they sold 28 millions, and this year, of course, they're going to sell more. Okay, so and this is Samsung's Galaxy S3, the latest cell phone. You can see how many chips they are, and then in a small package, there are 3 kinds of chips: analog chips, digital chips, and RF chips. All of them will interfere with each other. Okay, so you can put all these chips in a small package and then make it work. It's not that easy. Okay, and of course, to make this design reliably, and that's how you can get your competitive advantage, right? Okay, notice this is a printed circuit board design. Okay, of course it's not a 2-layer board, probably a 4-layer board. I'm not sure. Okay, so to be able to design, to be able to put all the chips together on the printed circuit board, that's what I want to. This class is about. Okay, how you can put all these chips together, connect them together, and then reduce noise as much as possible so that your system can work reliably. Okay, so that's your competitive advantage. Everybody can do functional design because the software is so easy to use and so smart. Okay, to compile your circuit, Verilog circuit onto FPGA, that's not a big deal nowadays, right? And then to write a Verilog circuit description to describe a circuit, to do a simulation, and then that's not hard at all. So functional design of any of this, or the principle of design, and then the knowledge of designs, and they're not that difficult. But to put everything together in a small package, very crowded package, and then to make it work, that's getting harder and harder. Okay. And this is Apple. Apple has anechoic chambers. Look, this is a person inside that chamber. Okay, and Apple uses this chamber. It's probably, if you look at this person, if this is 2 meters, this is about probably 20 meters, right, across. Okay, and this is the chamber that Apple uses to study, of course, the RF design, the antennas, and also their interferences. Okay, so and this is pretty neat. Okay, and somebody is sleeping there, so inside that chamber, because this is called anechoic chamber. Basically means there's no echo. Okay, and if you have a cell phone that transmits signal, and then all the signal transmitted will be absorbed by the walls. So if you have a receiving antenna, the receiving antenna will only receive the signal from this cell phone. It will not receive any reflections. Okay, so I like this very much. I figure this chamber is probably about $10 million. Okay, yeah, it's a very, very expensive chamber. Okay, and then I'll follow cell phone companies, and then these are some of the very active cell phone companies. RIM is also a very active in high-speed design. Okay, and Nokia is really in big trouble. Okay, yeah, I'm not sure Nokia can survive. Google Phone, and there's Nokia works with Windows Phone, right? Okay, so if Nokia goes and Microsoft goes as well, right? Microsoft does not know how to do phones. Okay, so Sony is already Ericsson and Sony. I think they combine together, and I don't think they're going to be a competitor. And what is this HCL, the Taiwanese company? HTC, yeah. HTC may be a good, may be able to survive. Okay. All right. So this is just basically, you know, almost like 10 years ago, Intel tried to push up the speed of their microcontrollers, and then it stopped right there, and then it started to do multi cores, parallel computing. Okay. So, and the speed of everything is about 3 gigahertz. That's recent, very much what people are designing with. Okay, 3 gigahertz. Remember, 3 gigahertz wavelength is 300 divided by 3 gigahertz, right? So 10 centimeters, right? The wavelength. Okay, so this board, if you design 3 gigahertz, transmit 3 gigahertz through this cell phone, and it's about 1 wavelength long. Okay, so you cannot treat this as a lump circuit anymore. You have to treat this as a transmission line. Okay, and then if you look at all the frequencies, everything's pretty high. Okay, and then everything is going into gigahertz range. Okay, this is pretty old news. Okay, in the lab, people have tested 10 gigabit second Ethernet. Okay, and it's possible. Of course, depending on whether the cost is cost effective, that we don't know. Okay, so 10 gigabits per second Ethernet is possible. Okay, but of course, if you can transmit at 10 gigabit per second, you should be able to receive it, right, or process it at 10 gigabits. Otherwise, it doesn't make sense. Okay, and Fujitsu actually tested a transistor that can switch at 50 gigabit per second. Okay, that's very high. And then you can do it on the chip, but if you cannot bring the signal out at that speed, it still doesn't make any difference, right? So pretty soon, we're going to design board level 10 gigahertz signals, okay, with 10 gigahertz signals. That's possible.